Okay, welcome. Thank you for coming. This is a talk that we call A Brewer's Guide to Filtering Out Complexity in Churn, or you can call it the Coffee Machine Talk. Our goal today is to show you how to remove the bitterness caused by complexity from your applications. Over the next 30 minutes, we're going to show you how complexity sneaks into your application, how to recognize it before it becomes painful, and how to get rid of it permanently. So we're going to introduce ourselves and then we'll get going. Hello again, I'll go first. My name is Alan Ridlehoover. I use the pronouns he, him, and I have 13 years of experience with Ruby. Also, I grew up in Seattle, so there's coffee like in my veins. And my favorite is a sugar-free vanilla oat milk latte, which is very Seattle.
Hi, everyone. Can you hear me well? You can hold that for me. Thank you. I'm Fito von Zastrow. I use the pronouns he, him. And I've also been using Ruby for a little bit over 13 years now. I'm from Asunción, Paraguay originally, but I live in the San Francisco Bay Area now. And if there's one thing I love as much as I love Ruby, it's coffee. My favorite is a dark chocolate mocha. Now, Al and I work together at a company that you might not expect, given that this is a conference for Ruby developers. We work for Cisco Meraki. We call it the largest rail shop you've probably never heard of. But we've also been friends for over 10 years now. Yeah. And we've worked together at 3 different places. We also like to get together and code on the weekends and drink coffee. Well, I have to say, we've seen over the years that we've worked together, we've seen code bases of different sizes and different amounts of complexity. But we'll get to that. You grew up around coffee, didn't you?
Yeah, kind of. Grew up in Seattle, so. And in fact, when I was a kid, I was fascinated by these mechanical coffee machines that my dad had in his office. You drop in a coin, you listen for the clink, you make your selection, and then the machine would just spring to life, hissing, clicking, and whirring. And when that whole automatic ballet ended, the final sound that you would hear was the splashing of that black aromatic liquid into the cup. Say magnifique. Now these days, I'm more fascinated by the inner workings of software. We both are. And like that coffee machine, there are all kinds of hidden complexity inside code. But software doesn't start off that way, does it? How many of you have worked on a greenfield application? Wow, most of you. Awesome. How did that feel? Lovely. Love it. How about a legacy application? How many of you worked on legacy code? Just about as many. How did that feel? Rough, challenging. We agree. In our experience, greenfield development is completely enjoyable. There's nothing in your way. It feels fast. You just move quickly. But developing in a legacy application does feel harder. Why is that? We believe it has to do with complexity. We think that there's a threshold which you cross at some point where the complexity becomes so much that you have 2 choices. Either you can live with the complexity as it grows and development slows down more and more until you just halt, or you can pause temporarily to reorganize the code and speed up development again. Now, we've seen organizations go down both paths, and when you take the path of living with the complexity, what do you think happens? Developers get frustrated, and they often blame the tools. And so you'll hear people say, I don't want to use Ruby anymore. It's just too messy. But it's not Ruby's fault. It's the complexity. And we did that to ourselves. So what we're going to do is we're going to show you how to take that second path, take the red pill, and remove the complexity, and then fall back in love with Ruby. Okay. Are we ready? We want to build a coffee machine?
Let's do it. Right. So how does complexity get into your code base? Well, the answer, of course, is it happens one commit at a time. So let's take a look. Now I'm going to move through the next slides pretty fast just to show you the shape of the code as it grows. And as the code gets longer, the font size will get smaller. So don't try to understand the code. It's made up anyway. And also, and this is important, we're skipping tests here for the sake of time, but in reality, we would not do any of this without tests. So let's get started. All right, here's the first commit in our coffee machine. At this point, the machine does one and only one thing. It serves coffee. First, it will dispense a cup, then it heats the water, it prepares the grounds, then dispenses the hot water, and finally, it disposes of the grounds. Now, this works great, but turns out not everyone likes coffee. So to increase our sales, let's add tea. All right, here we've added a conditional to determine whether to serve coffee or tea. And in the process of doing that, we added some duplication. The dispense cup, heat water, and dispense water steps are all duplicated between the two beverages. So naturally at this point, let's dry it up. Here's the dry version of the code. Now with both coffee and tea in production, we're starting to get more feedback. And turns out the most frequently requested feature is to add sweetener. So let's do that. Here, we've added sweetener just after dispensing the hot water. Now, of course, not everyone wants sugar, so we're gonna make it an optional ingredient here. Okay, we push this out, customers like it, and now they want cream. Since we already have a pattern for optional ingredients, let's just dispense the cream right after we dispense the sugar. All right, and for our next feature, it turns out that some folks don't like coffee or tea. Let's give them something else, like cocoa. All right, and so here we follow the existing pattern and added cocoa to the main if statement. But there's no need to add milk or sugar since the cocoa mix is already sweet and creamy. So let's exclude those optional ingredients when the customer is requesting cocoa. All right, and finally, who doesn't like whipped cream on their cocoa? And heck, I even like it on my coffee. The baristas look weird at me, but I really like it. So let's add it. Okay, so whipped cream is an optional ingredient that no one wants on their tea. So let's add it after the other optional ingredients and exclude it when the customer is requesting tea. Okay, so here we are, 7 commits into this code base, and we've already got 9 conditionals in one method. Now, at this point, this is still relatively simple to understand and work with if you're the only one working on it. But if you're part of a larger team, code like this won't scale. The reason for that is future developers will just keep adding, like following the existing patterns, adding more conditionals with each new feature, and that's going to cause the complexity to skyrocket. And our little coffee machine has been so successful that it was just purchased by a big national soup chain. They want us to add soup to our machines. Now, that's going to add a lot of complexity to our code. So let's pause here and evaluate where we are before trying to add any more features. Alan, can you take us through that?
Yeah. So we've reached an inflection point in our little coffee machine's life. How can we tell? What is it that tells us that we need to pause and reflect? Well, the first hint is that we had to keep reducing the font size to get that method on the screen. Method length is definitely an indicator that things are getting complex. Sandy Metz, author of Practical Object-Oriented Development in Ruby, has a rule about it. She says methods can only have five lines of code. In addition to method length, we also look at method complexity. This is a quantitative measurement of how difficult it is to understand a piece of code. Our preferred metric is called the assignments, branches, and conditionals metric, or ABC metric. The higher the number, the harder the code is to understand. We use a gem called Flog by Ryan Davis to help us calculate this number. Flog actually is a little bit more than ABC. It's got some Ruby specific stuff in it, like it penalizes metaprogramming, for example. And it calculates those scores for every method in the application. So we end up with this long list of scores. But how do we know what a good score is from a bad score? So way back in 2008, a guy named Jake Scruggs, who happened to write the metric food gem, wrote down these numbers for the Flog score of a single method. Now, over the years, we've used these numbers as our guide, and they're actually really effective at helping drive our code towards simplicity. So how does our little coffee machine fare? These are his strings, not mine. So let's go back through the commits in the code base and look at complexity over time. So our first commit weighs in at a complexity of 5.0. That's in that awesome zone. The churn number you see here is the total number of commits to this file. That'll become important later. All right, so adding the conditional logic for T with all that duplicated code really shot up the complexity. Now we're at 13.5. We're no longer in that awesome zone, but we're still below 20, and that's good enough. So after removing the duplication, the complexity dropped way back down to 10, which seems like a good thing. But this is really where things started to go wrong. Notice how we've intermingled the two algorithms. Now it's harder to tell what it takes to brew coffee or steep tea. You can't just look at it and say that's what it is. So, but from Flog's perspective, the algorithm's perspective, it's just doing math. It can't tell that we intermingled these algorithms. It doesn't know that it actually got worse. And this is a valuable lesson. What this tells us is that there's no magic metric that can light the way in every situation. Rather, there are tools that can inform our decision-making. So pay attention to how hard it feels to add new features to your application. If your intuition is telling you that it's getting harder, that it's slowing down, it's probably time to pause and reflect on your design. All right, next we added sweetener. This was our fourth change. Complexity rose back up to 12.3. We added creamer. That took us to 14.6. Cocoa pushed us all the way up to 19.6. That's just under good enough. Let's see where that last feature puts us. All right, to top things off, we added whipped cream, and that pushed the score to 23.4. Now, if we look at the trend line, we can see the complexity has reached a point where it's curving upward. That's not a good sign. Plus, we are over that 20 good enough line. So there you go. There's 3 ways to know when it's time to pause and reflect on a piece of code. Method length. Anything over 5 is forbidden by Sandy, so keep it short. Method complexity. Anything under 20 is good enough, but anything over 60 is getting dangerously complex. And then, how does it feel? If new feature development is slowing down, it might be time to pause and reflect on your design. So that's how we knew we'd reached this inflection point. It's time to start thinking about reorganizing this code before we try to add any new features to it. And that's what Fito is going to do right now.
So, we broke Sandy's rule, we crossed over Jake's good enough line, and we also intermingled 3 algorithms there. That all sounds pretty dire. But is it? Can we turn this code around? Yes, absolutely. Let's look at how. All right, so here's the method as we left it a moment ago. Now, code that's dry too early can lead you in the wrong direction. So let's undry this code or add back the duplication to see if there are any missing abstractions hiding in plain sight. Now, we call this practice rehydration. But before I show you what that looks like, it's important to know that you can't do any of this without tests. It's dangerous. For the sake of time, again, we won't be writing them here from scratch, but ensuring there's good test coverage for your code is the first step towards reducing complexity. We really like this tool called SimpleCov. I'm sure a lot of you have seen it before. We use it to ensure that we've tested every line and branch of code in our applications. As you can see here, we have 100% line coverage, and that's great. But we also have 100% branch coverage, which means that we're testing both sides of every condition. And that is very important when you're going to rehydrate code to make sure that you're not accidentally changing the conditionals. It's going to give you that confidence that you're safe to push your changes up. All right, so this is where we left the code. Since we've confirmed now that our tests are backing us up, we're ready to rehydrate the code. And that looks like this. All right, obviously, this increases duplication, but that's what we need to do in order to find these missing abstractions. Now we can clearly see each recipe, and since there's no overlap in the algorithms anymore, we can safely extract each one into separate polymorphic classes. And that looks like this. Now, as you can see, we moved each recipe into its own class. One for coffee, one for tea, and one for cocoa. The structure has a couple of big advantages. Each algorithm is now separate from the others. That means that if you should ever need to modify one of them, let's say to fix a bug or add a feature that's specific to one beverage, there's a much lower risk of you introducing a regression that would affect the other ones. You're only changing that one beverage. Plus, the Venn method is much simpler now. Now, you might have noticed that there's duplication between the classes. The calls to dispense cup, heat water, and dispense water are all present in every class. We actually want that duplication. It makes understanding each of the algorithms much easier, since the whole algorithm is there for each beverage. So we do not want to dry up the algorithms per se. Rather, what we want to do is we want to ensure that there is only one implementation of each of these methods. That's really what's meant by don't repeat yourself. It is perfectly okay to call a method multiple times. It's preferable, though, to only implement that method once. Now, Ruby provides multiple options for doing this. We could introduce a module, put all these methods there. We could use composition, have a class that handles all these and pass them in. Or we could introduce inheritance and put the methods in the base class. Now, in this case, because we're using these polymorphic classes and because we're unlikely to need these methods elsewhere in the application, we would probably go with inheritance, just put in a base class. All right, we're almost done. There's two remaining problems though. The first one is that the Venn method has multiple responsibilities. And second, it's not open-closed, meaning that you have to go and modify the code in it in order to extend it or add more functionality. So let's take a look at the responsibilities issue first. Its only real responsibility should be to prepare the beverage. But right now it's also picking which class should instantiate so that it can prepare the beverage. And that's the job of a factory. So let's introduce one. All right, so here we've pulled class instantiation out into a factory class. Now its only job is to choose which class to build based on what drink was selected. Now the Venn method only has the one remaining responsibility, which is to prepare the beverages. And it is now open-closed, meaning that we'll never have to modify the Venn method in order to extend the functionality of the coffee machine. The Venn method is now open for extension, but is closed for modification. However, you probably noticed that we just moved the open-close problem to the factory. And we introduced another issue there. The build method in the factory might return nil, causing the coffee machine's Venn method to throw an undefined method error. So let's solve that first. And we're going to do that by introducing the null object pattern, like this. So as you can see, the factory returns a null beverage by default. The null beverage is just a class that has a prepare method that does nothing. As for the second problem with the factory, it's still not open-closed. If we wanted to add a new beverage, we would have to go modify the if statement and add another one. We're going to solve that by using a different kind of factory. So here, we've converted the if statement into a hash lookup. Now, the build method is open-closed. And adding a new beverage only requires us to add an entry to that beverage's hash. Plus, because the factory is now hash-based, we actually, and this is a nice side effect, it goes from O of n to O1 when looking at the beverage class. Okay, so let's take a look at where we are now with the complexity. And let's start by revisiting this graph. So here's where we left off after adding whipped cream. And then the next thing we did was to rehydrate the code. Now look at how much more complex that was than the dry solution. But remember, the dry solution was hiding the fact that there was a missing abstraction. So this is just intermediary complexity. So next, we pulled the algorithms out into their own polymorphic classes. And this dropped complexity significantly. And finally, we extracted a factory object. And now the complexity is lower than it's ever been. We're now well back in the awesome range, and the vent method will never need to change again. Now, let's take a look at all the other classes in the app. There are 6. Now, the coffee machine has settled down to a very low complexity of 2.2. Now, coincidentally, the factory also weighs in at 2.2. And there are 3 beverage classes that are all more complex, but they're well within the good enough zone. So there's really nothing more to do there. Except that there was a reason why we did all this. We needed to add soup to our coffee machine. And we wanted to do so without making it more complex. So here's where we left off. Just add some soup. There you go. I'm going to pause and let you take a look at it. So adding soup did not require us to change any of the existing methods. You probably noticed that we added a new class all the way there. And we had to add it to the list of beverages here in the hash. So now some people consider this open-closed because the only change to the factory was to add the new class to the beverages hash, which is configuration. You're not changing logic. Now, we're a little squeamish on calling this open-closed because you did have to go and change code in that class. So we have a preferred method of doing this. And that is actually to have the beverage classes register themselves with the factory. That looks like this. So here we've extended the beverage factory class to introduce a register method that the beverage classes can call when they are loaded. And this will add the class to the factory. And now there's no longer a separate hash that you have to manually maintain. In fact, this solution is now truly open-closed. We can expand the functionality of our coffee machine without having to modify any existing code. You just need to add a new class. Here we added apple cider and nothing else changed. Now, if we wanted to, we could also hide that registration bit behind a little DSL. Let's take a look at what that looks like. So here's the little DSL. We just introduced a base class. We call it beverage, and it defines a prepares class method that does the registration for you. And now the individual children of the beverage class can just call prepares instead of calling the beverage factory.register method directly. Now, we really like this pattern. First and foremost, because it's more declarative. You can look at that class and it tells you, I prepared this. It's also a little easier on the eyes. Okay, so that was a look at a very small greenfield application. But you're probably thinking, all right, that's a toy example. Your applications are obviously a whole lot bigger and a whole lot more complex. So how will you know where to start when you get back to work? I'm going to hand that over to Alan.
Thank you. I'm glad you asked. So we've really only looked at method complexity so far and watching how it grows as the file changes over time and paying attention to it so that we can prevent complexity from becoming painful and slowing us down. But you can also use complexity combined with churn to find problems across your entire code base. So as we mentioned, complexity is the measurement of how hard it is to understand a piece of code. Churn is the measurement of how many times that bit of code has been changed. So we like to think of it like this. Complexity represents how much pain you're going to experience the next time you touch that file. And churn represents how often you are inflicting that pain on yourself. So let's take a look at how to use churn and complexity together to evaluate your whole code base. To find the areas that need the most attention in your application, plot complexity and churn like this using a tool like Code Climate or the Ruby Critic gem. This kind of churn versus complexity chart was first proposed by Michael Feathers, who's the author of Working Effectively with Legacy Code. And we use this kind of chart ourselves to locate the areas in our code base that need an intervention. To understand the chart, let's break it into quadrants so that we can look at each one. Down here in the lower left is the pain-free zone. These are files that are easy to change, easy to understand, and in a healthy application, most files live here. The upper right quadrant is the painful zone. These are files that are hard to understand, hard to change, and prone to regression. Now, being aware that these files are in this quadrant will help you make decisions about where to add new code. You probably don't want to add new code to these files. In fact, if you do need to modify these files, prefer extracting code out of them over adding code to them. When you extract the code, you're creating a new file with a churn of 1. So that's going to pull that down into the pain-free zone. This will create simpler classes throughout the application. So down in the lower right are the low complexity files that change frequently. Now, it's possible that these files are actually just configuration data masquerading as code, like JSON hiding in an RB file or something. So if so, try to move that ever-changing config data out of the code into a file that the code can then read as it needs. And finally, the upper left quadrant is high complexity files that rarely change. This is likely what Sandy Metz refers to as an omega mess. An omega mess is a file with a big scary algorithm that never needs to change. Sandy's advice in this case, and we agree, is that you should just leave these things alone. Don't touch them. They're not causing you any continued pain because you're not touching them. And if you do screw around with them, you're likely to introduce a bug. So just leave them alone. Now, these quadrants are helpful to think about, but reality looks more like this. Now, the red line represents the pain threshold. Anything in that pink zone is going to be resistant to change and prone to regression. This file is in need of the most attention. It's super complex and it's being modified all the time. Extracting hidden abstractions from this class will simplify the entire application. But there's no need to tackle all that complexity at once. Try improving the code a little bit each time you touch the file by extracting something. Also, you may not want to start with that file. It's super complex, and maybe it makes more sense to start over here. This will give you a chance to practice some of the techniques we showed you, like rehydration and the self-registration, without having the pressure of working on that most complex file in your system. So that's the story of our little coffee machine, how complexity snuck in, how we recognized it, and how we removed it. Let's wrap up with some key takeaways and a bit of homework. So there are 3 things we want you to take away from this talk. First, complexity will sneak into your application. It happens one commit at a time, so you've got to be vigilant. Pay particular attention to conditionals in your code. They could represent objects trying to escape your method. And remember, dry is about method implementation, not invocation. As my friend Josh Clayton says, don't make your code so dry that it chafes. Second, you can recognize complexity before it becomes painful. Keep methods short, watch your complexity, and pay attention to your intuition. If methods are longer than 5 lines, or your flog scores are over 20, or it just feels slower than it used to, it's probably time to pause and reflect on your design. Third, you can back away from that painful complexity. Leverage polymorphism and factories to enable you to add new features to your application without having to change any existing files. Rehydrate your code or reintroduce some duplication to help identify missing abstractions that can be refactored into the polymorphic classes. So those are the 3 takeaways. Now, here's what we want you to do with that information. First, find out what your average method complexity is using flog. It's a simple gem. It's got a command line. You guys can figure it out. I'm not going to show you how. Second, find out which class has the most churn in your application. It's a churn, it's a gem, same thing. You can figure it out. And then finally, we want you to figure out which class needs the most attention in your application. Now, show of hands, how many of you already know which class that is? I bet more of you that actually know that that's the one. That's the problem class. But go ahead and confirm your suspicions with the tools. And then finally, let us know what you find. Here's how to reach us. Feel free to write, tweet, or toot. Actually, you're more likely to get an answer if you toot. We don't really do much Twitter anymore. You can also subscribe to our blog if you're so inclined. Also, if you want to walk your way through the little coffee machine application, you can find it with tests on GitHub here. Plus, you can check out our other personal projects while you're there, including RubyFlog, which is a VS Code extension that will put the flog score for the selected text, the current method, or the average score for an entire class down in your footer. All right, one last thing before we go. We did mention that we are from Cisco Meraki and that we are probably the largest Rails app you've never heard of. We don't build coffee machines, but we do build internet machines for coffee lovers. Both Starbucks and Peet's Coffee use Meraki devices to put their customers on the internet. Our 17-year-old Rails monolith has over 2 million lines of Ruby code. It's very old, yes. It's also super complex, yes. And it handles billions of requests per day, and it supports a multi-billion-dollar business. If you're interested in solving really hard problems related to code complexity, software design, and large-scale Rails deployments, you should come chat with us. We're always looking for more great Rubyists. All right, here's a list of our references and influences. Feel free to take a picture, or the slides will be up soon, I'm sure. If you have any questions, come find us or drop us a note. And that's it. Thank you. Thank you so much to Becky and Spike.
Yes, is there like a DK algorithm or some way of like, if you have a very old code base, like the one Alan just mentioned, 17 years old, you're going to have some files that just have tons of commits. The way we usually run this analysis is we look at the last 6 months, and that gives us a better picture of what code is changing right now. If something doesn't show up in that window of time, but it has like tons of churn, it's probably an omega mess. Probably was changing at some point and now it's settled. But you can change the window of time depending on your code base.
Yeah, so the question was, is there a trade-off with focusing on method complexity versus the overall application complexity? And I will say, when you look at the method complexity, like what am I holding in my head right now? Right now, I'm focused on that method that I'm writing. So that's where I want to focus on the level of complexity. When I get to understanding, like we broke those classes out into polymorphic beverage classes. Each one of those was easy to understand in its own right. And overall, the application, the total complexity went up because we added like code around those things. Instead of an if statement, now there's a method and a class declaration and all that. So the total complexity of the application, if you measure it with flog, went up. But the thing that I'm holding in my head right now, that I'm working on right now, is always a method. It's maybe a class. And in those particular cases, we find it really a lot easier to understand when we focus on the method complexity. In fact, we don't even look at total complexity. Usually we look at average method complexity within a class. That gives us the ability to focus on what we're actually thinking about right now. Admittedly, more classes, more smaller things than you're like. We have this argument at work sometimes with some of our less. I don't know. There's folks at work who are very much interested in seeing the entire application in one method. Like they just want to see the whole thing. I just want to see it all and get the whole thing in my head. Well, there's 2 million lines of code. You're not going to do that. It's just not going to happen. So I'd much rather be able to get the class in my head first. So I want small classes, and really the thing that I'm working on right now, the method. So
yeah,
that answers your question.
One thing I would add is that, like we mentioned, this is a tool that gives you information on your code. Like it's not the only metric that you should look at. So if you find yourself writing small methods and you have multiple classes, but you still feel like making a change is hard, then you should listen to that intuition and maybe think about how the objects are organized. There are other tools that you can use to graph like a dependency tree of your objects and maybe take a look at that. Like, do they have too many dependencies? You're right. There's a whole other aspect of like the system at large and how it can become more complex.
Yep, one more. So the question was, are there any tools that would help you identify complexity that's coming not from the method complexity, but from the multiple layers of abstraction that you're introducing? I think the dependency graph is helpful. I don't remember the name of the...
I'm trying really hard to remember the name, but I'll put it in the Slack channel later. There is a tool that we've used. Fun fact, it doesn't work with our application is so large that when you try to render it, it just explodes. Like it literally, it has an animation where it tries to like be cute and move around the classes. Ours just goes like... so we've had to like section off code and see like, okay, what are the dependencies over here? But I can post a link to the tool.
We've been doing this a while. Like I said, we've been working together for 10 years. We have over-abstracted things. It has happened more than once. We didn't learn. And usually the best indicator of that is when the coworker who didn't write it with you walks over and says, "What the hell were you thinking?" So that's always the best indicator. Anyway, thank you very much.